This is Andy Barrett of polyphys.com, introducing an app that calculates what I call potential symmetry. I came up with this idea while thinking about creativity in machines. When it comes to artwork, machines are great at certain things. They're great at finding patterns and producing patterns. And I was thinking that creativity affords you the ability to create outside of any pattern, which is obviously a prerequisite of being unpredictable. So in keeping with those ideas, we can ask the following question. Given a set of points in a 2D space, where can we add a new point such that the symmetry of the resulting structure is minimized? And I guess this was supposed to be equivalent to asking, what's the most creative place to put a new point? The opposite would be, what's the least creative place to put a new point? That is, where could you add a new point such that the symmetry of the resulting structure is maximized? To answer this question, we'd need some measure of the symmetry, or rather the potential symmetry, of putting a point at a certain position. And that's exactly what the plot on the right shows, with red and blue corresponding to high and low potential symmetry. The way I calculate potential symmetry is inspired by X-ray diffraction studies of glasses. I was pretty fascinated to learn that even though glasses have atoms at completely random positions, scientists figured out, I guess like 50 years ago, that you can use X-ray diffraction to measure the statistical properties of nearest neighbors in the glass. What I want is some measure of the overall symmetry of a point set. To get this, I simulate diffraction to produce a frequency response graph like the one shown in the bottom left plot, and then I measure how random the graph is. Highly symmetric structures will resonate better, so the frequency response function will contain sharp resonance peaks in this case. So I can use the existence of these peaks to measure how symmetric a structure is. This calculation is performed for every colored pixel in the potential symmetry plot, using each pixel position as the location of the potential point to be added to the point set. You can adjust the resolution of the potential symmetry plot. You can adjust the resolution and range of the frequency response calculation. In the diffraction simulation, you can adjust how much the signal is attenuated after each reflection, and using this order control, you can put a cap on the number of reflections to calculate. The potential symmetry calculation is pretty expensive, but you can make it go faster by lowering any of these controls here, or, of course, by keeping the number of points to a minimum. You can create a new point by clicking anywhere in the space, and you can delete a point by simply dropping it on top of another point. Additionally, there are these two buttons. The left button toggles backscattering, which, if it's included, will also make the calculation a bit slower. And the right button toggles between two modes, representing different ways of calculating the randomness of the frequency response spectrum. Well, that's it for this app introduction. Go to polyphys.com to play with this app and many more. And if you like my work, then please consider making a donation to keep this project growing. This is Dr. Andy Barrett of polyphys.com. Thank you for watching.